Okay, suppose G is acting on X. Now, what is a group action? That's the mapping from G cross X to X, such that all you know that for all X in X, identity element fixes this, and for all X in X, G1, G2 in G, G1, G2 dot X equal to G1 dot G2 X. Okay, so if these two properties are satisfied, then that's a group action, and you know that group action may be very different. You just note here, even though all of you know that here X is just a set, and the set may have no structure at all. But when it has nice structure, then by looking at the group action, a lot of information can be obtained. Okay, so we assume now that X is a nice space. I mean, connected, you know, locally connected. Okay, Hausdorff. Oops. Hausdorff. Second countable. You know, topological, maybe also locally compact. So it's a nice, so it's like a manifold, okay? Locally compact, topological space, e.g. X a manifold, all right? So X is a topological space, so we can, and G, a group acting on X by homeomorphisms, and the map, I call it phi. Phi is continuous. So you can assume all these. So that means you can give G a topological structure. Okay, and yeah, you can also think of G as a topological group coming from this action. But we will not assume anything other than this at the moment. Okay, so now there are two. So there is a so to each group action, you have orbit, that is set of all points which are images of X under the group action, and stabilizer, which is a subgroup of G fixing X. Okay, so this is a subgroup, all right, but this is a subset of X. Okay, so this is the difference between an orbit and a stabilizer. And if you know elementary group theory, it is also, I mean, you can, so, I mean, I at the moment, let's not write anything. I just write that okay, I just write the G, I mean, this is a set theoretic bijection with the cosine. So the orbit of X has a set theoretic bijection with the cosine group G mod Gx. All right. Now, yeah, so there is a natural cosine map pi, which is X to X mod G. So this is the orbit space. So this is equal to, you know, Gx let's write like this, such that x in x. Okay, so this is the space. So you are considering every orbit as a point, and that gives you a new topological space. And this map is defined in a manner that a subset in the image is open if its inverse image is open in X. Okay, so that gives you it a quotient topology. Okay, so okay, so that means this map. Okay, so this map gives nice structure, okay, on X mod G if X is nice. Okay, okay, so let's keep it there. So now there are two definitions that we used in the previous lecture, and also I think you might have seen in yesterday's tutorial. Okay, so these are general definition you can define for any group action. So yeah, so one thing, so I am writing on an electronic board, so in case you don't see it properly, you can just interrupt me and tell me. Okay, otherwise to me it looks okay. Okay, but if you have any technical difficulties or I am not audible, etc., please let me know. Okay, so let X and G be as above. Okay, then G is set to act freely on X if whenever Gx equal to X for some X in X, that implies G is identity. Okay, so this is a very basic definition that we need at the moment. And then G acts, sometimes people call it properly discontinuously or simply discontinuously if for each K in X compact, okay, the set of elements in G whose orbit of K has non-empty intersection with K. So this set, why this is happening again and again. So this set, oh, I see, I understand. This set is finite. Oh, sorry. So I see that how this works. I mean, why this erase button was coming again and again. Okay, so okay, so this is the definition of the pre-action and the properly discontinuous or simply discontinuous action. All right. So now this is a theorem that you have also seen in the previous lecture. I was very quick in the previous lecture. So let X be a, I assume here X is a manifold, okay? And gamma a, but this sort of theorem holds for general topological spaces also, nice topological spaces. But here you assume it's, I think we will assume it's a manifold, okay? Assume X is a topological manifold and gamma a group of homeomorphisms, okay? acting on X, then X mod gamma is a manifold. Okay. And further, this is what we proved on the, not proved, we discussed in the other class, that this is a covering map if and only if.
Here gamma acts properly discontinuously or not? Means
Yeah, let's wait. So
okay.
further, X to X mod gamma is a covering map if and only if gamma acts freely and properly discontinuously on X. So to argue that X mod gamma is a manifold, you don't need any proper discontinuity. But if the action is not free and proper discontinuous, then the quotient map may not be a covering. And we would like actions where the quotient map is a covering space. I hope I have answered your question. Yeah?
Yes.
Okay. So now this is what we have roughly seen so far. Okay. So now I will change, maybe I change my color here. Okay. Okay. So this is what we've seen. So now, okay, so which color is looking better, black or blue? Any suggestion?
So black is better.
Okay. Now you assume XD is a metric space and gamma is a group of isometries acting on XD. Okay. So, oops. Okay. So where we are here. Okay. So now assume that we are now in a much more nicer space where we have a metric on X and gamma is a group of isometries acting on X. Okay. Now natural question. So under like what we have seen for topological spaces, can we metrize X mod gamma? Okay, so can we metrize X mod gamma? Okay, so we consider the following map. Okay, so we have a natural map from X mod gamma cross X mod gamma to the real line defined by, okay, defined by the original metric. So what you do, you take two orbits, okay, and you just define it to be distance between the orbits. Okay, so here this is distance of set. So I hope everybody knows here metric space, right? So it is the same sort of game that we are playing here, that if you have a metric space, you can also define metric between two sets by taking the minimum distance of or infimum distance of all points. So here we are taking that distance. Okay. So now one observation. Okay. So is it a well-defined notion? I mean, okay. So so let me just observe that. Observe that d of gamma x gamma y equal to dx gamma y. Since if given gh in gamma, d of gx hy is same as d of x g inverse hy, because we gamma is a group of isometries, so that's why. Okay, just give me 1 minute. Okay, so so this is the reason. So the infimum of the both sides, infimums of the both side are equal. So this is a observation that you keep it in mind. Okay, so now we will use this observation somewhere to prove that maybe one proposition. So let gamma x d etc. okay are as above. I mean, you know what I mean. Then d of gamma is a metric on x mod gamma if and only if each gamma orbit is a closed subset of X. Okay, so now let's try to see if we can prove it. Okay, so first assume d gamma is a metric and consider gamma x not equal to gamma y. Now, since d gamma is a metric, d gamma of gamma x gamma y is greater than 0. So this implies d of x gamma y, because of what I have just observed, this is greater than 0. Okay. Now let d of x gamma y equal to epsilon. Then this means what? B of x epsilon is contained in x minus gamma y. All right. So that means gamma y is closed. Okay. So this gives you one direction. Okay. Now conversely. Conversely, assume that each gamma orbit is closed. Okay. Then, I mean, clearly, d gamma of Yeah, so d gamma of gamma x, gamma y greater than 0. Okay. Yeah. So well, the gamma x, gamma y, I would say greater than equal to 0. Okay. So now you have to prove that if they are equal, then the metric is 0. So now if gamma x not equal to gamma y, then d gamma x, gamma y, you can check that this is greater than 0. Okay. Since x does not in gamma y and gamma y is closed. Okay. So you can actually separate these two orbits, okay, which will give you, okay. Yeah, so now you can, now one can argue since x is a manifold, okay, that d gamma of x gamma y greater than 0. So that will prove that it is indeed a, you know, it satisfies one axiom of the metric. Now clearly d gamma of gamma x gamma y, this, okay, and then I leave triangle inequality as an exercise. So this proves the proposition. Okay. So but the punchline is that if you have a group action where gamma orbits are closed, then you can actually pull down the metric of x to the metric of y. Okay. So now a few more observations. Okay. Observations. Okay. So let gamma acts discontinuously on x. Okay. I mean, here we have a metric space xd. Wait a minute. So, okay. Discontinuously on xd. Okay. On xd. Okay. So then first observation, that stabilizers are finite. Why? Okay. So recall stabilizer of gamma x is gamma in gamma such that gamma x equal to x. Now, since x is compact, what will happen? Since x is compact, so, well, so since x is compact, what will happen? You know,
by proper discontinuity.
Yeah, since x is compact, by discontinuity, stabilizer of gamma x is finite. Okay. And the second assertion, what I want to so each gamma orbit is a closed discrete subset of X. Okay, so this require I mean, yes, let me prove it. Okay, so proof. Okay, so before giving the proof, maybe I can make a definition. Yeah, I just make a definition first. Okay, so before giving the proof, let me first define something that will be used later. So we will prove it, but first a definition. Okay, a collection S of subsets, okay, of a topological space X is called locally finite, okay, if for each X in X there exists an open neighborhood U of X in X such that U intersects only finitely many members of X, such that U meets only finitely many elements, I mean, of S. Okay, not X, but S. Okay, so now it's a small exercise that, you know, so a subcollection of a locally finite collection is locally finite. Okay, and you know, if you take a so the union of a locally finite collections of closed subsets is closed. So this is essentially, you know, general topology and what I have just defined here. Okay, so now I will try to prove. So now proposition. Okay, if a group, okay, I mean, let's not write too many things here because we are limited in time. Okay, so gamma x d as above. Okay, oops. Then each, okay, so assume gamma acts discontinuously on X, then each gamma orbit is a closed discrete subset of X. Now we will quickly prove this. Okay, just a minute. Yeah. Okay. So let X be a point in X. Okay. Now assume, I mean, what do we want to show? We want to show that, so claim collection of Gx such that G in gamma is locally finite. So this is the claim. Okay, so that you take 1 point subsets from the orbit, then they are locally finite. Now suppose that is not so. Okay, if possible, not so. Okay, then there exists Y in X such that a neighborhood of Y meets infinitely many points of gamma X. All right, so what does it mean? Okay, so now since X is a metric space, that means you get a so you have Y and you have a locally finite neighborhood where you have infinitely many elements from the orbit, and you have a metric space. So you know that in a metric space, if you take a small open ball around a point and you get infinitely many points from a sequence, then that converges. So this means there exists an infinite sequence Gi of distinct elements from gamma such that Gix goes to Y. Okay, so then K Ax Y, G1 X, G2 X, and so on. This is a closed subset, and this is a, this is a closed and bounded subset, right? So this is a compact subset of X. So this is, or even otherwise, you can directly prove. I mean, you don't need a closed and boundedness. You can prove directly that every open cover of this K has a finite subcover. So K is a compact subset of X. Okay. So now, but you see, observe that Gi of X is in K intersection Gik for infinitely many I. This is contradiction to discontinuity. All right. So that means gamma X such that gamma is a locally finite family of closed subsets of X. Now, by the observation that union of locally finite family of closed subsets is also closed, okay, this implies Gx, which is Gx means not Gx. What is I mean gamma X. Okay, so gamma x such that this, okay, so union of these, okay, right? Yeah, so maybe I write it in a better way somewhere. This is closed. Okay, now since every subset of gamma x is closed in X, implies gamma x is discrete. Okay, so this is the proof of the result that if you have a continuous discontinuous group action on a metric space, then each gamma orbit is closed and the stabilizer is a stabilizer is a discrete subset. All right. Okay. So now a more general result actually holds. Okay. So theorem. So any question so far? Okay, so there is no question. Then I can write down the statement. So let gamma x d be as above. Okay. Then gamma acts discontinuously on X if and only if each stabilizer subgroup of gamma is finite, each gamma orbit is a closed discrete subset of X. Okay, so we have already seen one direction, right? We have already seen one direction, all right? That if you have a continuous group action, then we know that each stabilizer subgroup of gamma is finite, and the gamma orbit is a closed discrete subset of X. Okay, so now we have already seen one direction, the other direction needs to be proven. So you assume that 1 and 2 holds, but the action is not discontinuous. Then you get a contradiction. Okay, so proof. One direction we have already seen. To prove the converse, assume 1 and 2 holds, but the action is not discontinuous. Okay, so we would like to get a contradiction to either of these. Okay, so suppose gamma is not discontinuous. That means what? That is, there exists a compact set K such that gamma in gamma, gamma k intersection k. So this set, you know, so this set is not finite. Okay, so there exists a you know, sequence. So there exists a sequence gamma I in gamma such that gamma I k intersection k non-empty. Okay, we can also assume that gamma I is not equal to gamma j inverse in that sequence. Okay, you can assume that just by isometric property, that the one I have described. Okay, so what does it mean? Okay, so that means there exists xi in k such that gamma I xi in k. This is true for all I. So for each I, you are getting an element from the compact set and you are getting an element from the corresponding orbit. Okay. Now k is compact. So since k is compact, every sequence converges, right? So there exists x in k, y in k, such that xi goes to x and gamma I xi goes to y. Okay. So now apply triangle inequality. So now consider d of gamma xy, which is less or equal to gamma ix, gamma ixi plus d of gamma ixy, which is same as d of xxi plus d of gamma ixy. All right. So what does it mean? That means your xi, so that means d of gamma xy goes to 0. Okay. Now we have yeah, so there are infinitely many. Okay, so since gamma ix equal to gamma jx implies gamma j, this is identity. Okay. Observe that there are infinitely many gamma x which are distinct. Yeah, here we have used the property that the stabilizer is finite. Okay. Yeah. Yeah. So by 1. Okay. Stabilizers are finite. Okay. So now you choose a subsource. So that means we can choose a. Okay. So we can choose a subsequence of distinct gamma ix such that gamma ix tends to y. So what does it mean? So this implies in your orbit, you have a sequence which is convergent. So this contradicts assumption 2. Okay, so this proves the theorem. So we have proved that a group of isometries acts properly discontinuously on a metric space if and only if the stabilizers are finite and the orbits are closed discrete subsets of X. So here is the complete proof that we have given. Now, quickly, let me come back to my original question, when we can metrize X mod gamma. So corollary, okay, so let gamma acts discontinuously on a metric space XD. Then X mod gamma D gamma is a metric space. So this is an immediate corollary to this theorem, and one of the results that I have proved at the beginning, that that X mod gamma is metrizable if and only if you have closed orbits, right? So that's what we have proved at the beginning. So this too gives you some idea. Yeah. So now one question maybe that I should sorry, I just close the rotation here somewhere. Yeah. Okay. So now we know that X mod gamma is a metric space. Okay, and we have the quotient map. Okay, so now what can you say about the quotient map with respect to the metric? So I will answer you the question, but before that, I will remark that, also note that the metric topology on X mod gamma agrees with the quotient topology. Okay, so just you just try to see it. You can see it. So now, what can you say about? Okay, this is inside bracket. Okay, this has nothing to do with the original question. Okay. So now, what about this? So the answer to this question is given by this theorem. Okay, so let XT be a metric space and gamma is a group of isometries of the metric space that acts freely and discontinuously on X. Then the quotient map is a local isometry. Now, what is a local isometry? So local isometry, that is Pi is a map that has the following property. For each x in X, there exists r greater than 0, such that pi restricts to this ball okay, this is an isometry. Okay, so this actually gives you a nice description of the quotient map with respect to these two metric spaces. Okay, so now, so what does it mean? That means now let's come back to our manifold. So maybe a corollary. So let X be a connected manifold. Okay, manifold equipped with a metric D. For example, X a Riemannian manifold that Arindamda has spoken in his first lecture. Okay, so let gamma is a group. Let gamma be a group of isometries acting freely and discontinuously on X, then X mod gamma is a manifold and by okay, so why does not, yeah, so it's okay, just a minute. Where is my I can come here. Okay, yeah, so and pi X goes to X mod gamma is a covering map which is also a local isometry. Okay, so now the proof of the theorem I think is not difficult, but I will skip the proof. Okay, I mean, yeah, so let's not give you the proof at the moment. Okay, so now what I will do, yeah, so I will quickly introduce what is a hyperbolic space. All right, so this is a general machinery that we will use. Okay, so now I will just change the topic and I will come to my to what I promised you, that geometry of hyperbolic space. Now, is there any question that you want to ask in the meantime? Then probably I can quickly tell you about it. Is there any question?
Just I have a little query just to Krishnendu.
Yeah.
The very interesting theorem and corollary you have stated just. But if it is only freely, then what happened? It will be not hold, no? The relation. You have considered that acting freely.
Yeah. If it is free, okay.
Only free.
then I think you can still say that X mod gamma will be a manifold.
Yeah.
Okay. But
Okay.
this may not be a covering in that case.
Yes, yes. That means the discrete spaces you will not get.
You will not get
Yes,
this.
yes.
Because we want our manifolds to be
Mm.
sent by discrete subgroups, right? So,
Yes.
so,
Yes.
so yeah, so
Okay,
that's actually a
Yes.
good point that you have raised here. Yeah, so let me just maybe I will not describe hyperbolic geometry at the moment. Yeah, so what I will do here, oops, why it is not coming? Yeah, here it is, let's come. So that's actually something which I was about to say, but I forgot about it. So Ananda, is it okay if I take maybe 5-10 more minutes?
Yeah. No problem.
Okay.
Okay.
Yeah, no, because my schedule is up to 7 o'clock, and it's already late,
Yes.
right? So yeah, but I just take maybe 5-10 more.
Okay. No problem. No.
Okay.
No.
Okay.
Continue.
So now, as Arindamda has pointed out about discrete subgroups, right? So, well, I mean, whenever you have a group of isometries of a metric space, you can give that the structure of a topological group. Okay, and as a topological subspace, you can consider subgroups which are discrete. All right. So now the question is how discreteness and properly discontinuous action, these two are related. Okay. So now here I would like to just state a result that, so first definition. Okay. So a metric space is called finitely compact if closed balls are compact. Riemannian manifolds, for example. Okay, yeah. And here is a theorem. Again, I am stating without proof. Theorem. So let X be a finitely compact metric space. Okay. And gamma is a group of isometries of X. Then gamma is discrete if and only if gamma is
discontinuous.
Yeah, gamma is discontinuous. Okay, but so if you want to take only discrete subgroups, then it is enough to take discontinuous action for the kind of good spaces we are considering. But if you want X mod gamma to be a manifold, then the action has to be free. Otherwise, there will be these singularities and cone points. They are the action. Yeah. So thanks for